Okay, so good morning, and so today we have lecture 12, and so recall that we studied the statics part of statistical of classical mechanics, and the problem came down to finding some generalized coordinates. Okay, so today we will add dynamics to story. Okay, so dynamics is time. So from our viewpoint, when I use the word dynamics, it means time evolution. Okay, so we'll need some principle, and we've already seen a more general case of arbitrary dynamical systems. Okay, so there what we had is we considered some the capital X variable, which is x1, x2, whatever, to xn, and equations of motion would be some dx by dt, which would be some vector function. So this is also a vector of x and possibly time. Okay, so we've already seen this, but we will consider not this class of systems. So we will consider a subclass of systems, okay, for which dynamics is specified differently. Okay, and so here the principle is called Hamilton's principle. Okay, so the system, according to which the system evolves in time from initial time t1 from qa of t1 to qa of t2, where again is some later time t2 in such a way that an action functional is minimized. Okay, so the input for dynamics here is an action. Is this clear? So this is what we are going to do. And so why is it a subclass? Because something like this may not be necessarily writable as, as coming from some extremizing some action. Is this point clear? So S will be, and we will also restrict ourselves to S of QA such that the action, you can do more general actions. So Hamilton's principle will still work. Is of this form. Okay. So for instance, in the last assignment, we had something where it was Q double dot, but as I explained in words, or you can look up Goldstein or any other standard book, if there is some, if the Lagrangian is a function of QA double dot, then you can add one more variable and make it into first order derivatives. So again, you just will increase the number of degrees of freedom. Okay. But you need not do that, as we saw in the assignment. Okay. So is this clear? So extreme implies Euler-Lagrange equations of motion. Okay, so for all A equal to 1 to n, so n degrees of freedom, we just get different equations. It just says dl by dqa minus d by dt of dl by dqa dot equal to 0. So there are n equations, n, so these are n possibly coupled equations. Solved with the boundary conditions. That is QA at T1 and QA at T2 are given. Okay, so are there any questions, comments at this point? Everything is clear?
Yes, sir.
Okay, thank you. Okay, so you can see that there is so again we did something in the assignment, and we saw that so in problem set 4, we studied 2 examples. And saw how a particular solution, a particular trajectory or whatever, extremized, actually minimized the action. Okay. And in the harmonic oscillator problem, there was something interesting. In the simple harmonic oscillator example, we found that what did we find? We found that that the solution was not unique. Okay, but so there are. How do we? I mean, we would like to make the solution unique. Okay, so this is the question. Any ideas? So in that example,
I thought that we can obtain the unique solutions by applying the boundary conditions only.
No. So in that example, I think QD was the solution. It was some cosine something, right? To that, if we had, we could add we could add something with sine. We could have added something with arbitrary amplitude. So let me look at that problem set. Just give me a second. What was QD? Yeah. So QD was.
Sir, actually, Tanay pointed out that they were actually both the same. The boundary conditions were actually both the same, but actually physically they are different. One we are specifying at t is equal to 0, another we are specifying at t is equal. At capital T.
Yeah. So let's look at that. No solution. I just want to look at it. Okay. So this is what we did. Plus 3 was the solution, right? QD was that, and we were given that Q at 0 was 1,
and Q
at 1 was
5,
right? Okay, so somebody said that to this, let's consider Q tilde of t, which is QD of t plus A sine pi t. Okay, you can check exercise.
Yes, sir, it will.
Right? Right. So check. You can check that it solves the Euler-Lagrange equation of motion. Okay, and boundary condition it satisfies because this thing at 0 and pi sign vanishes. So what we get is A is unfixed. Okay, so is that correct?
Right, sir.
Okay.
Yes.
Yeah, but interesting thing is now you compute the energy. Okay, and you should find, what you will find is that it will depend on A. Actually A square, okay, but okay, it will depend on A square. Okay. So the thing is, if you specify, so one can make the solution unique by specifying the energy. Okay, so there will be, basically what will happen is there will be one contribution to the energy coming from here and one contribution to the energy coming from here. The cross terms will go away, I believe, or you can time average or whatever. I mean, no, you can do that. Yeah, you get two identical contributions, two different contributions, and you will find that. So you will see that if you can ask what is the energy when A is 0. Okay, so this is actually very interesting. I mean, it says that when you solve the Euler-Lagrange equation, there might be some ambiguity, but actually what you will discover is that there will be only it's not like there will be plenty of cells. There will be some, parameter of solutions here. There is, I mean, there are only two terms, right? So I'm not counting this freedom in A. What I'm saying is that there will be only some classes of solutions which you can add to this setup. Okay, so that's all I want to say. So coming back to this is, so now we will return to this. No, I want to have white on here. Okay, so maybe specify some additional data. Okay, to make it unique. Okay, that is answer 1. So that's what we did here. We are saying we specify energy. Okay. Answer 2 is also interesting. Answer 2 is that there exists an equivalent description. Okay. Called where we can convert the problem to an initial value problem. Okay, and that will the initial values will be, you give me all the QAs at some initial time, but you also give the QA dots or the momenta. You specify this. Okay, so and there will be evolution of, so this will be like your X now, and so we'll have some equation which will look like dx by dt equal to something. Okay, so this description will not have this ambiguity. Okay, and by the way, this particular thing which happened for in this example, it has to do with the specific boundary conditions that we had. Okay, it went through some cycle. So if you had chosen, instead of 1, if you had given the boundary condition at some, 0.7 or something like that, right? Then you would discover that this uniqueness, you will recover uniqueness in this example. That's a second way of doing that. Okay. So what has happened here is that there's exact period such that this just doesn't modify things. Okay. So it's just a coincidence. So, but generically, okay, so however, but generically we'll see. No, I don't want to make any statement about genericity. Okay. All I want to say is this thing. So this method, this is the Hamiltonian description, which we will do at a later stage. Okay. So, and the remark, we already seen, I've already made this remark that the action principle connects up nicely to quantum mechanics. So, action principle or Hamilton's principle. So, so the Feynman path integral approach to quantum mechanics generalizes the action principle. But the Schrodinger, so-called Schrodinger or Heisenberg, description of quantum mechanics is more natural in the Hamiltonian framework. Okay, don't worry if you don't understand any of these things. It's more like general knowledge which you keep in mind. Okay, that's all. Okay, so what we're going to do now is we'll do some examples. We'll do some examples. Okay. So the first example is already there in the problem set 4, particle moving in a arbitrary electromagnetic field. Okay, so particle okay, so we know from the equations of motion, we know this very well. We know that this is equal to Q. Right, so this is the Lorentz force law. Okay, so in PS4 we saw that the Lagrangian. What was the Lagrangian? Yeah, that the Lagrangian is given by okay. So this Lagrangian is actually, I mean, at least to me, it's like, so the remarks which we have for this is, the first remark, which we already made last time, is that, the okay, so this is important. It's important that we cannot write it in terms of electric fields and magnetic fields, but we have to use the scalar and the vector potential. Okay, so this is the first observation. Second thing is that let's compute the momentum, generalized momentum, of course. So what does it say? We have to do dl by dxi dot. Okay, but now you see that where does xi dot come? There are two terms where it comes. This term and this term. Both of them came. Okay, so what we get from this is that the I, this is definition, and this is equal to m xi dot. This is something we know. but this will give us plus Q into A. Okay, so P vector, we can write this as MV plus QA. Okay, so again we see that the generalized momentum is not mass times velocity, and this is not special relativity or anything. It is just particle is just Newtonian. Nothing, there are no speeds comparable to this. Okay, do you appreciate this? Okay, so if you look at this, you will see that velocity mv is p minus q times a. So this is the velocity. Okay. And so you should remember that this is always going to be our definition of momentum. Okay, momentum is not m times v. Okay, this is the second comment. Any questions or comments? Okay, so the third point is a much more general thing. Are Lagrangians unique? If we are given Euler-Lagrange equations of motion. Okay, answer is no. Okay, but it's very interesting that we can quantify some of the non-uniqueness. Okay, so let L prime be the following. L, so we are given, given one Lagrangian, we know it's Euler-Lagrange equations of motion. I will construct a second, okay, so we'll construct a second Lagrangian which will have the same Euler-Lagrange equation. Okay, so plus, okay, d by dt of some function. So I'll write it for one variable, but you can generalize it to multiple variables. Some arbitrary function. Okay, claim L and L prime lead to the same equations of motion. Okay, I leave it as an exercise check. Okay, but you need one formula which you should be careful. Total derivative versus partial derivative. Please bear that in mind. So this will be df by dt, that is differentiating with respect to the second variable, plus, okay, df by dq times q dot. Okay, so this is the from calculus. You will need this. Okay, but I will prove. So what we will do is we'll study the actions. I will study the actions because I gave you an exercise to check that L and L prime have the same equations of motion. Okay, so before let's finish this proof. Okay, so if you look at S prime, what is that? It will be integral from t1 to t2 dt of L prime. Okay, so this quantity is what we will call S. So this is S plus, but this is a total derivative, so this is just f of q and t evaluated at t1 and t2. Okay, so this is what? So S prime and S are not equal to each other. But question to you is, what is this quantity? Is this a known number, a known quantity, or it's a function?
It's a number.
It's a number. Okay, because in the Lagrangian formulation, you're given Q of T2 is specified for you. Q of T1 is also given for you. So these are all numbers. Okay, so S prime and S a constant that is completely independent of the trajectory. Okay. So in other words, it knows nothing about the trajectories. So we know that so it doesn't matter which trajectory you put, S prime minus S will give the same answer. So it's boring. So this constant. So this is, so what it says is that this constant has no meaning. Okay, and if you extremize, if something extremizes S, it will also extremize S. So if a trajectory extremizes S, it also extremizes S prime. Okay, is this point clear?
Yes, sir.
Okay, very good. So now back to the particle in a magnetic field. Okay, so there what happens is that the scalar and vector potentials are not unique. Okay, so we can have two sets of these things. So this will, if you input this, you get L, and if you input this, you get L prime. And this is exactly what we showed. We showed in the class that we saw that what we saw was L prime minus L was just d by dt of lambda was that so-called gauge parameter. Okay, so it's a total time derivative. Okay, of course we know that the Euler-Lagrange equation is completely in terms of E and B. So if phi and A and phi prime A prime gave the same E and B, Euler-Lagrange equations do not change, of course, right? Because they give the same E and same B. And we have been told in our BSc or other electromagnetism courses that it doesn't matter. You make some choice and you proceed. Okay. So what we see is that it fits into this general setup of saying that if two Lagrangians differ by this thing. So one important point here is not, if you see that it is not a function of q dot, it's just a function of q and t. If it were a function of q dot, total derivative, then this won't work. I mean, right? because there will be a second, there would be also one more term which we could not. We don't know in the initial value problem, in the Lagrangian problem, we don't know q dot, right? We only know q at t1 and q at t2. Okay, and you'll also start seeing that if this function at q dot, one more d by dt of it will give you a q double dot. So it takes you out of that kind of the Lagrangian setting which we assumed. Okay, so this is the third point which I wanted to emphasize, and comment here. The quantum mechanical story is even richer. Okay, so just a comment. Okay, is richer again. I need not write more. Yeah, it is not a course in quantum mechanics. Okay, so we'll do a second example. Okay, and this is to illustrate why holonomic constraints are nice. Okay, we already saw, we saw the double pendulum. Okay, which was of this kind. Two masses connected by some rigid rods. Okay, this is a kind of object. It was 2 degrees of freedom. Okay, but if you try to solve it, solve it as we did in high school, you would say, there is some tension here, T1, there's another tension to T2, mg acts this way, m1g acts downward. And then again here m2g. So you would do free body diagrams. For m1 and m2 and solve the forces and solve for T1 and T2, and then from that we will get the dynamics, right? Isn't this how we used to solve the problem? Okay. So tension is an example of a constraint. Of a force due to constraints. What is the constraint here? That this thing has some length L1, this thing has some length L2. Right? So these are the constraints, and the corresponding things are tensions. But what we saw in problem set 4 was that, nothing, we didn't need to do anything. We just work out what the kinetic energy of M1 is, what is the potential energy, and all the details of the constraints were used, of course, to get only 2 degrees of freedom. And lo and behold, we were able to solve the problem. Okay, so the Lagrangian methods are actually very, very powerful, especially when there are constraints, at least holonomic kind of constraints. Okay, so now we will do another problem where we will try to solve. Hopefully this will become a circle. Yes. The wrong thing is moving. Okay, great. Okay. So what we have is a hoop of radius r. Okay, and there is a bead. Let's use some other color since we have so many colors. Okay, so there is a bead of mass n, which is restricted to move. On the hoop. Okay, so let's do some, and gravity acts of course in the z direction, so we'll choose this as the z direction, and for now let's choose this as x. Okay, so yeah, so the first step is to just go ahead and we want to do the dynamics of the hoop. So the problem is do dynamics of the hoop, of the bead. Okay, so let's do some things. This is behaving funny. Okay, we'll live with my poor straight line. Okay, so let's say this angle is theta. Okay, and say the position of the bead, this is z, and this is x, and this distance is r, right? So we have x upon r equal to sine theta. Okay, and of course, what is z by r? Rather, x r minus z by r is cosine theta. Correct? Okay, good. So now we'll make the problem more interesting. Hoop is now spinning about the z-axis. Okay, and this will be our origin, of course. We want to choose this as 0, 0. And okay, so we're going to spin this about the z-axis, and the question is, how are we going to discuss the dynamics? So okay, is the problem clear? Okay. So let's do the statics of the problem first. How many degrees of freedom?
Two.
1. 2.
Yeah, so somebody said 2, so we'll come back to 1 later. So 2, what are the degrees of freedom?
So first is where the bead is on the hoop, and second where the hoop is correspond to the z-axis.
But that's a given number, right? It's some constant. Omega is given to you, so there's no equation to it. It's a constant,
okay,
right?
Then it reduces to 1.
Only 1, right? So it's only 1. Okay, correct. I mean, naively you would think 2, but we are just saying this hoop is being rotated with constant angular velocity. So if you know it at some time, after that there is no, I mean, nothing. It's a trivial, this thing. So effectively, it's 1 degree of freedom. Okay, I'm not going to say that 2 is totally wrong. Okay, but 1 is kind of 1 degree of freedom, and we can choose it to be theta or x. Okay, and for rotating, we can replace it by rho. Okay. So let's just focus when it's on the xy exact plane. So if it is x, we know that we get something like this, x plus okay, so this is a holonomic constraint. Okay, we've all done this, but it's useful to be explicit. We don't have to give the z coordinate. If you give me theta, okay, we know. Okay, but actually x is not so great because there is a second position which is here, which will give the same value of x. Okay, so theta might be better in that sense. You agree, right? Or z might be better. Or z might be better. Okay, so x, well, that's a square root. Okay, that's what happens. Okay, so x has a twofold. Okay, but theta doesn't. Okay. Okay, so let's first okay, so let's just do the following thing. So for a moment, ignore the rotation, and we'll try to solve the problem. Okay, so let's let z be. Should I do z or theta? Yeah. So let theta be our generalized coordinate. Okay, so what is the kinetic energy for the problem? It's half m x dot square plus z dot square. Right? But we saw x equal to r sine theta, and what was the relationship between z and this? R minus z, is it? Yeah.
So you said that theta might be better than x. You were talking about it, means since x has a twofold problem, that is why you were saying like that, isn't it?
Yes.
And that is also the reasoning behind choosing theta as the generalized coordinate.
Yes. So theta is better than x. That's all I'm saying. Okay. So from this we can just work out what x dot is. X dot is r cosine theta, theta dot. And this will tell you minus z dot equal to minus r sine theta, theta dot. So if you plug it in there, what we get is half m, okay, m r square theta dot square. This is t. And what is the potential? Some mgz, right? We can put that. And z equal to and the Lagrangian is simple, it's t minus v. Okay, so we are done. So we know how to solve this problem. Right, so once we are done this, it's easy. And just think about it. I mean, if we had tried to solve this problem like we did in high school or whatever, it'd be too hard. here, I mean, all the constraints have been already put in. Once we have done this, all constraints have been taken care of. We were also careful in how we chose our this thing. Okay, so we get something very nice, and we are done. So now we are going to include the rotation. Okay, so now it will be a 3-dimensional problem. Now it's a 3D problem, but it's better to work in cylindrical polar. Which is rho, which is square root of x square plus y square, phi, which is tan inverse of. Okay. So the constraint, the holonomic constraint is very simple. We just replace x square by rho square, right? So that goes through. So we just can write out what is T now. Okay. What is T? This is something we worked out already, so I'm just writing it. Okay, but we are also told that phi dot, what is phi dot? It's equal to omega, right? Because it's spinning with constant omega, so we can just write that. And what is the potential energy? It is just I'm writing it in terms, I'm choosing rho now as my coordinate. Okay, so L is again T minus V, which you can go ahead and write. I'll stop here. But what I want you to see here is that the kinetic energy here, what was the kinetic energy in this full term? Now what we are seeing is that there's a term which is half m omega square rho square, which is like a function of rho, and we would naturally think of it as some kind of potential. Okay, so exercise obtained the Euler-Lagrange equation of motion before tomorrow. Okay, so we'll continue this problem. This is a very interesting problem. What we'll find is that the dynamics, there is depending on the value of omega, the behavior is different. Okay, so we'll see. So what we get here is an effective one-dimensional problem with a funny potential, which is getting a contribution from the kinetic energy term as well. And but it doesn't matter where it comes from. It's a one-dimensional problem, and we'll work out the equations of motion. And we'll do some stability analysis, and we'll study this. Okay, so I'll stop here, and I'll pause for questions.
Sir, in the problem of choosing generalized coordinates, we said that omega is a constant, and then we reduce the degree of freedom to 1.
Yeah.
So isn't that the mixing of dynamics with the statics?
No, like I said, it's your style if you wish. We could have kept phi as a extra degree of. So in this way of thinking, rho and phi are the degrees of freedom. Okay, and so what you will get is d phi by dt equal to omega. That's one equation. That would be the second Euler-Lagrange equation if you want. It's not even it's an equation which you can trivially integrate. Which is this, right?
Okay.
This is that equation. So I've gotten rid of things. Right?
Yeah, I got it.
Okay. So rho also has the same twofold problem, but anyway, that's not a big deal. We can take care of that. So, but we know how to take care of that. But let's just forget about that twofold problem. But then we have this action. Okay. So, any other questions?
Hello.
Yeah.
Yes, sir. You last time said that about symmetries. Last time that symmetries that change Lagrangian unchanged, that will lead to constants of motion.
Conserved
this time,
yes.
This time you said if we change Lagrangian by total time derivative, that will lead. That's same physical problem basically. So can we say that such transformations that change Lagrangian by a total time derivative will also lead to constants of motion?
No, okay. It's probably one. I mean, there are symmetries which don't even give you. So, how do I say that? No. Generally, adding df by dt may not correspond to a symmetry. But there are situations where f is 0, the symmetry itself, and there are situations where f is non-zero for a symmetry. So you will act by the symmetry and you will get something new, and the difference between these two will be a total derivative, like we saw in this thing. But there's really no symmetry it's some gauge principle in the case of, so in general, it won't be associated with symmetries. But there are subclasses of things which will lead to symmetry. We'll see a little bit more examples. And when we talk about Noether's theorem also, we will see. Okay?
Okay, sir.
Sir?
Yes.
When we defined our generalized momentum as dou L by dou x dot, can you give us some more intuition on this? So, what will be the force here? Will it just be the time derivative of this?
Yeah. So actually, that's so generally, what happens is that so there is this whole formulation of classical mechanics, which is pre-Lagrangian. Which I am not going into. Okay, so where you will appreciate that, I think. So there will be a T, and then you will write something like d by dt of q dot, and d by dt equal to generalized forces. Okay, for instance, the magnetic field story will fit into that kind of thing. Okay, so this way, generically, potentials won't depend on velocity, etc. But this is the kind of story one would do. But but for me, E being defined to be dl by dq dot is just a definition.
So, suppose two balls collide in this magnetic field. This new P will be the conserved quantity, not just mv, right?
What is two balls collide? What is that?
Just elastic collision happens, momentum is conserved, right? So
total momentum is conserved.
Yeah. So total momentum, do we take the?
Yeah. So actually, the alternate way to see this is that which goes this way, is that translation symmetry, okay, implies momentum is conserved. Okay. Okay. And if you ask what is the momentum which is conserved, you will get this quantity. So,
okay.
So, for instance, if you take the case of a particle moving, if you take the case of a free particle in special theory of relativity, that the action is different, right? It's not half mv square, but it is that square root of 1 minus v square, which is square root of free factor. So, in that case, that is the momentum which is conserved, not Okay, so it goes back to a nice connection. We'll also see that there is a sense in which this is the momentum which generates translations. Okay, what that means we will see in the Hamiltonian formulation later in this course. Okay, so there are many reasons why this is the correct definition.
Okay, sir.
Okay.